Hey everyone, so today I have my friend Alpha again, and he's going to be putting me through another coding interview. So, Alpha, do you want to quickly talk about what kind of coding interview you're going to put me through today? Maybe what we might focus on? I mean, you don't have to make it super specific to DP. I think just generally
hmm
just want to keep practicing lead code, so these mock interviews is help keeping me a bit sharp too.
Yeah, so I've been doing like the 2K plus problems, so I'm just gonna give you some of those. I have
No
some
way.
easy ones, some harder ones, depending on how you do.
2K?
And
Elo?
2K,
Oh
2K, ELO. So we'll
my
see how it goes. A
God.
lot of them I think are pretty straightforward. Some of them are kind of hard. So we're gonna start with like an easier one, and then yeah, depending on how you do, I have four, and then we'll just kind of see how you do. If you do the first one super fast, I'll ask you a harder one, things like that.
But you see my Elo right here is 1500.
Yeah, I gotta bump that up, dude.
Alright, let's try it out.
All right. Plus, like people have been saying, you get better by being challenged, So if you just keep doing binary tree traversal or something, never
You're right.
gonna. So
This is what I need. This is what I need.
all right. So we'll start off with this one. Oh, actually, I can add you to the actual problem.
Yeah, add me. And just send the link. Everyone go subscribe to Alpha. He's been dropping sick content.
Wait,
Let me look at
create a link. You can only join. Okay, for some reason I
Hello
can't
and
make
welcome
it.
to
I
another.
don't know why. Let me see.
someone.
Oh, it's because I'm in one. Okay. Okay.
People
Yeah,
are
they have this really dumb thing on here where like it doesn't just like
leave you in.
auto kick you out of a join like when you're done, even if you close a tab or anything. It's kind of annoying. Okay, I got it. So
Guys
can
trying
you
to
join this
ramp
one?
up my elo. That's
You
crazy.
gotta ramp it up, dude.
Hards. That's crazy. Okay, okay.
Yeah, so all these are mediums and hards.
What's
So
the elo of
yeah.
this one? Like just flat 2000?
Oh, so there's another thing I found. It's actually a Chrome extension. It's called LeetCode difficulty rating, and if you get it instead of like the medium or whatever, it'll actually give you the rating. So I think it's really nice to start using it.
Wait, I'm gonna send you a room link. For some reason, it tweaked out when I used mine.
Okay, that's fine. But yeah, I would recommend getting that sometime in the future because yeah, literally like instead of the hard or whatever, it actually has a rating, so it's kind of convenient.
And it like uses zero track to figure out the rating, or does its
I
own
think
thing?
so, yeah, because it says 2008 for this one. Yeah.
Okay, awesome. All right. Okay, let's get. Let's. Is this a math one? Because I cannot do math one.
It's not a math. You don't need any math. I
Okay.
mean, there might be some math thing, but it's not required.
All right. Okay. So we're taking on some 2000 Elo questions.
Yeah.
All right. Let me parse the question. So a die simulator generates a random number from 1 to 6 for each roll. You introduce a constraint to the generator such that it cannot roll the number I more than roll max consecutive times. Given an array of integers roll max and an integer n, return the number of distinct sequences that can be obtained with exactly n rolls. Since the answer may be too large, return it modulo 10 to the 9. Two sequences are considered different if at least one element differs from each other. Okay, so let me take some notes here.
Yep.
We're given a we're doing a die simulator, and we're building a die simulator, and we need to. I mean, the die has what you can roll 1 to 6. Roll one to
Mm-hmm.
six. We're given a roll max, so we and the roll max is 1, 2, 3, 4, 5. The roll max is 6 elements. Six elements, and I'm guessing it's like indexed based on like we could only roll for this. So if roll max is this, right? That means we could only roll one time, one consecutive time, right?
Yeah, consecutive. Yep.
So we need to see the different number of sequences with exactly n rolls. So we're given n rolls. So what are the different rolls ways we can roll two? We or we're given n. We're given what's the number of ways we can roll n times. So I'm thinking it's like, okay, let's assume maybe we could roll 1, and then we can only roll 1 once, so maybe roll 2. That's 1. So that's one unique way. Is this, now I'm just checking, does this matter? Like, does the permutation matter? I guess it matters, or just answer. Oh, because we're talking about sequences, so the permutation probably matters, right? Because it
Yeah, so you
is.
can look at the examples, like especially example 1, and it'll make it kind of clear what that should be.
There will be 2 rolls of the die if there are no constraints on the die. There are 6 by 6 possible ways. Yeah. So in this case, looking at roll max, the number 1 appears at most once consecutively, and therefore sequence 1 1 and 2 1 cannot occur, or 1 1 and 2 2 cannot occur. So the final answer is, okay, you kind of remove that. There will be 2 rolls of the die. 36 minus 2. Well, let me see. Oh yeah, because you could roll these 2 and you could roll these 2.
Mm-hmm.
So these don't really matter. Like if it was, yeah, there's no constraints there. Okay, let me think. I mean, one way I'm thinking is straight up just brute force it, like a backtracking algorithm where we try the different roles.
Mm-hmm.
So like,
So what do you think would be the time complexity of a brute force backtrack? Just try everything.
well, what is n? N is 5,000.
Yeah, n can be 5,000.
I think it's limited to the branching. We could only use 6, and there's a roll max. It could lead to an exponential algorithm, but there
Right,
might.
like let's say roll max is like let's say n's like 5,000 and roll max is like 15. We're gonna get really big numbers. So
Yeah, it's already
can we do
huge.
better than like a backtracking?
Yeah, like brute, like the first thing came with brute force, but maybe we can either brute force, or I mean we could probably use like a, there might be a way to cache the results of the brute force
Mm-hmm. Yeah.
and do some sort of DP, and then like maybe there's even some math solution that I can't think of right
Mm-hmm.
now that might be able to just calculate them, because in the explanation here they're literally just doing math in order to
Mm-hmm.
figure out. So these are the different ways I'm thinking. Cache result of the brute force, basically a DP top down,
Mm-hmm.
and then worst case, even this DP top down could involve math
Mm-hmm.
to calculate, or just straight up just some math solution that's not coming to me right now. So
Yeah, so we can eliminate the math solution. There might be one. I don't know. We can eliminate the brute force as well because it's too slow. So can we do some kind of caching, DP, or some kind of thing like that? Yeah.
okay, so what we can do is, I mean, what are the different? Let me think of like how the DP. So in order to come up with a DP algorithm, I kind of need to look at how the brute force plays out and see where I can cache. It's kind of
Mm-hmm.
the way I approach it, because the brute force would be top down with no caching, right? So what I'm thinking is, we start with the empty list kind of thing, or the different options, and we're gonna build it to the leaf nodes. The base case is we've made 6 choices. Um, for okay, let's talk
6
about,
choices?
or n choices.
Oh yeah, okay. Yeah.
So the base case is we made n choices, and is
Mm-hmm.
there ever a case that we can't ever make n choices?
Oh, what do
Like
you
we ran
think?
out. I think there's a case where the constraints are too low that we couldn't even make n choices. But
So how would that look? Yeah.
I would
Can you give me an
say,
example?
So maybe we had to roll 5 times or 10 times, and the roll max was like 1 for each.
Yeah, so the roll max is max you can roll consecutively, not like the total rolls you have of that number.
Okay. Oh
So
yeah.
there's a yeah.
Oh. Okay, that complicates everything, or twists me out a little bit.
It actually makes it easier once you figure out like how it works. It makes things easier.
You can.
So yeah, you can roll infinite of every number. You just can't hit the
Okay.
max at any point.
But just not the max at any point.
Yeah. And so do you see now how you couldn't run out of numbers because you could just like pick another one?
Yeah. So what I could do is for each one is gonna branch out in the brute force, right? It'll branch out probably 6 different times, where you're
Mm-hmm.
picking like 1, 2, 3, 4, 5, 6,
Mm-hmm.
right? But not only are we branching 6 times, maybe we'll branch out. Maybe like I'll roll once, or I'll roll twice, or I'll roll zero, or I'll roll, like I'll for each branch. Pretend I'm gonna roll one here. I'm
Mm-hmm.
gonna roll one like once.
Okay.
I'm gonna try or like yeah, basically you'll try roll one once or two or one twice up to the max, right?
Okay.
And it'll branch out that many times per roll. I mean per like dice, like 1 to 6. We basically loop through 1 to 6 in that branch,
Mm-hmm.
and then we'll pretty much like the depth of this the depth of this will be like we'll go until the base case, which is n=6 kind of thing, or we'll the depth of the tree will be n. But yeah, that's what I'm thinking. Like kind of we loop through each options from 1 to 6 on each level,
Mm-hmm.
and then we need to pass down like some like we need to pass down who we can't use, I guess. Because once I use one once, I'm gonna assume that I'm gonna do 2 or 3 or 4 or 5, like twos or three, like everyone but one on the
Mm-hmm.
next level. But if I choose like two once here, I'm gonna do everything but two. But that might mess up our caching. So I'm
Yeah, so
trying.
ideally we want to like cache as much as possible. So if we do what you said, where we try to roll like one once, one twice, whatever, like let's say all these roll maxes are 15, you're gonna have a lot of branches there from like one state. Like you might roll 15 different amounts for every single number, which is like, like 100 or something. So can we do it in some other way where we don't roll that many times, but then cache? Like, oh yeah, I guess let's ask like what's the minimum? Like this is always how it is for these DPs. What's the minimum amount of information we need to store to make a decision?
Yeah, I think we just need to multiply it, right? We just need to know how many options I have here. So I can roll 1 6. Let me think. I think maybe we could. Oh, sorry. Could you repeat that?
Yeah, so in our like DP, we're gonna have some state like that we're storing and passing down. So what's the minimum amount of information we need to know to know where we are and like what decisions are possible? Like what's the minimum? Because the more information you store, the
The less
like worse
cacheable,
caching
right?
is.
Yeah.
Yeah, kind of like an extreme example. Imagine you're storing your location and like a lat long, and I store it exactly, then it would be kind of useless to store those things because it will be like so many combinations and decimals and stuff. It wouldn't be the best. So how can we like store the minimum amount of information we can while still being able to make a decision from that?
Yeah. Each one, I kind of need to know, um, like how many. Because what we can do is if each branch is already a roll. Oh, actually, we can't just do like 6 rolls in a row. We can't just do that because it needs to like each branch. If we want to branch up into n, each branch needs to make one decision. So I think we
Mm-hmm.
need to know number of rolls left
Okay, makes sense.
for each. So
So when you
we
say for each, can you clarify that?
for each dice. So we essentially need to pass roll max down. with -1 based on the last decision we made.
Yeah, so let's say we're on
Or
like
actually, or
yeah,
yeah, go ahead. Go ahead. Sorry.
yeah, I was gonna say like so for each die, we're only concerned about like not hitting this consecutive streak. So if we're on like number 1, we know we can roll everything other than number 1 as much as we want. Like we don't need that information, right? Does that make sense?
Wait, sorry. Could you repeat that?
Yeah, so let's say we rolled like a 1 previously.
Mm-hmm.
We don't really need to know uh how many rolls we have, like how many rolls we did for any other number, any other thing other than what we rolled before. Because we're only concerned about not hitting this consecutive limit. So if we know we rolled a 1, we know like everything else is just going to be fine. So we don't need to have like every roll left for every number, if that makes sense. Because basically the only time we can't make a roll is like if we rolled that previous number the roll max amount of times. Does that make sense?
Yeah, but like, how do we know? Pretend we're what I'm trying to think about right now is like when we're deep in the branch, and then
Mm-hmm.
we roll a 1. How do I know that I
Mm-hmm.
hit my roll max now? So that's why I'm kind of
Exactly. So what's the minimal amount of information you need to store? So you did point out like I need to yeah like what's the minimal amount of information you need to store to know if you hit your roll max or not.
that's what I was thinking. Like, because in when we're in a specific branch
Mm-hmm.
or a specific node in this like decision tree, we could be
Yeah.
either making this decision for 1 or 2 or 3 or 4,
Mm-hmm.
right? So I'm thinking that's why we kind of need to know the roles for every single one and just maintain like how much we have left for each one. Like we have like 1 roll left for 1, 0 for 2. But I guess
So how can we have that state? Like let's say for example 1, you have this roll max array. No matter what you rolled, only one of these numbers will be different than the roll max array, right? Like if I rolled a 1 before, the roll max changes, but all the rest are the same. If I rolled a 2 before, the roll max for the 2 changes. Like you don't need the whole array. You just need to know like what's the number you're concerned with hitting your streak for, because everything else won't change, right? Like anytime I roll another number, the roll max resets for the rest of them. Does that make sense?
oh shoot, I didn't even realize that. Yeah, every time I roll, I forgot about that. Every time a roll max, or every time we roll, we reset the max for all of them. So what I'm
Right.
thinking is like, so I think all we need to do is pass down the roll max. After we roll the roll max, we just pass down into the DP function. We pass down in our DP. We pass down obviously well in the DP we loop from 1 to n.
Mm-hmm. So
Then
when
we
you say 1 to n, do you mean like 1 to
1 to
6 or
6.
1
Sorry,
to
1 to
n?
6. Sorry.
Okay, yeah, okay.
We loop to 1 to 6, and then we probably pass like a variable gets passed down. That's
Mm-hmm.
just max rolls, or like rolls left,
Mm-hmm.
or yeah, rolls left. It's
So
like
what does this rolls like mean?
how
Like
many
what is this?
rolls left for
How many rolls do we have left for total or for the current number we're on?
maybe the current number we're on. So
Okay.
current number. So we need to pass down who happened before, which is probably 1.
Mm-hmm.
And then
Okay.
we'll be like rolls left is like maybe we subtract 1, we pass it in. So
Mm-hmm.
when we call DP, we'll pass in maybe the current number, which would be like the last choice,
Mm-hmm.
and then the rolls left,
Mm-hmm.
right? And then like when we DP into another option, then we kind of just cache on the current number and the rolls left. I don't know if that would work.
Mm-hmm.
Does it kind of make
So
sense?
how do we know when we hit our base case? Like on line 25, you said base case when I made n choices.
I think we just need to just keep track of like an options, or we just need to pass in like the path length. It's like
Mm-hmm.
if the path length equals n,
Mm-hmm.
we just return like one, because that's like one unique way to get down.
Right.
And then when we do the DP, it's like a for loop, and we're just adding up all the possible ones.
Mm-hmm. Mm-hmm. And then what would be the so we're caching on these three things. So what's the I guess what's the time complexity of the full function? So we have these three things and we're looping through 1 through 6. So can you estimate the time complexity of this full function before we start writing code?
Let's see. Well, the branching factor is 6. Like if we didn't cache, it'd be like 6 to the n, or wait, yeah. It's like
Mm-hmm.
the brute force would be like of 6 to the n. It's like now we're kind of caching, so it might be like O of n times 6. Wait, let's see.
Mm-hmm.
If we, like, I still don't really understand, because what I would do is like, I don't know how many problems are actually overlapping that it's actually going to cache on.
Mm-hmm.
Because if you know how many overlapping problems it's going to be.
Let's say we can have like all of these things. Let's just say, to make it simpler, all of these states can have every single number. Like let's say that's the case. All right. So current number can be anything. Rows left can be anything. Path length can be
Yeah,
anything.
okay.
So let's just say, like, what's the worst case time complexity
Yeah,
here?
I guess it's like n times like m, which is like the max of rows max, like the maximum value there,
Mm-hmm. Yep.
times like 6.
Mm-hmm.
So it leads to like an n times m algorithm.
Yeah. Yeah. And then we also have this part in the, so typically the way to calculate it is all of your states, assuming worst case all of them can happen, times whatever is in your function. So because we have another 6, like we're picking 1 through 6 die, it would be like this.
Wait, we have
Does
to
that make
multiply
sense?
by another 6?
Yeah. Because we have 3 states here, right? So current number is 1 through 6. Rows left is max, like you said. Path length is n. And then in the actual DP, we can also pick any one of 6 die, right?
Yeah. Okay.
Okay.
So what I'm thinking is, so we're gonna be doing we're caching on all three of these, so it's gonna be like a 3D sort of DP.
Mm-hmm.
Because yeah, path length kind of matters, because like if I already have, if we're only at 5, we only have one choice left to get to n. Like the number of paths is gonna change, so we have to.
Yeah, like if we don't have the path length, we never know when to stop. We'll just keep going infinitely.
Yeah.
So
And we need to include that into our DP cache,
Mm-hmm.
because in order to include it in our DP cache, or in order to actually cache results, like we need the path length to return the unique numbers properly.
Mm-hmm. Yeah, and so a quick trick you can use, I don't know if you're familiar with this, so you can do this estimation, then you can look at your constraints, and I think you need it to be below like 10 to the 8th roughly to pass. So if it's like rough, so like here n is like 5k, so that's like 10 cubed or something. M is 15, so that's another like 10. So this is like 10 to the 4th, and then these are both roughly 10, so you get like 10 to the 6th. So you can make these estimations when you have actual like OAs or problems, and then you can figure out like, will this TLE or not.
Awesome.
And it's kind of nice because you might make your estimation and then you can immediately say like, oh, this will just be too slow. I can't do this. Let me try something else.
Yeah.
Doesn't really work for like an actual like on-site, but for OAs or any kind of that, you can quickly get a rough idea.
Yeah. Cool.
Okay. So
I'll go
let's
ahead and
try
implement
to.
that. Holy crap, that was actually difficult.
Yeah. Okay. Let's. Yeah, I mean the main like the way DP's problems get harder is A, you have to do a bunch of stuff before, or B, the dimensions are really tricky. So this one's like not super straightforward. Like it wasn't just like, oh, I just have like an index and then like how many steps left there or something.
Yeah.
So, yeah.
Rows left. So I'm gonna create this DP helper function. and I'm gonna build like I'll have a cache which is a set. Then I'm gonna be like return self dot. Or we'll just do the DP here, and the current number is probably none. Wait, let's see. Because I'm trying to figure out the first one where we didn't. Okay, actually, the first number we'll just start with one. We'll just say one, and we'll just say the rows left. We won't actually reduce one. Rows left with like the 0th index, and we say the length is 0, and then we just pass in like this cache.
Okay, yeah.
And then let's just handle the base cases, like if the path length, and then we're gonna have to pass in n here. If the path length is equal to n, we return 1, because that kind of means like, yeah, that's like one path all the way down. And then we're gonna have like some result here, and we'll return the result, right?
Yeah.
And then here we're gonna have to do sort of the DP portion, which is looping through all of the options. So for the dice, in range 1 to 7, so we roll 1 to 6. What we're gonna do is for dice is 6. What we're gonna do is result plus equals self dot, or we're gonna say if the current number is equal to that dice and rolls left equal to 0, we're going to continue. That means we're at that current dice. That's the last one that we chose, and we don't want to do it, right?
Okay. Yeah, that makes sense.
Then we call self.dp, and then we're going to do this dice. It's like choosing this dice, and we do rolls left at that dice. And then we do that grabs the current number, the rolls left. What's the
path length is how many rolls you have total. So,
so we're gonna do path length plus 1, and then we're gonna do n. Right, and then we just do. We need to pass in our cache, which is gonna be current number, rolls left, path length. Okay, cache here. So what we can do is like it's a 3D DP. Where we store the current number, the rolls left, the path length. So we store that, and we just store the result. All right, that caches it. Now we do if this tuple is in our cache. It's in our cache, we return something like this.
Yeah, the nice thing about Python is like having more dimensions doesn't make it hard. You just add like another variable to your tuple and it's fine.
Pardon?
I was saying the nice thing about Python is like having more dimensions in your DP doesn't make it hard because you just add like another variable to the cache and it's
just finding out the DP though.
Yeah, for sure. So you have some problems. I didn't see which one you ran into.
Let's see. It's not super scriptable. Yo, John, how are you accessing the internet from where you're at? Okay, wait. This guy's like out of town. dp.nice. Let's see. Int object is not super scriptable. Okay, it's
so I think rolls left is not an array. Rolls left is a number in your code. So you're trying to like access rolls left, but it's a number.
I need to pass down roll max here.
Okay.
Right. So I pass in rolls left, and I pass in roll max here.
Okay.
Okay. Let me just debug that code real quick. What? Duplicate. Oh, rows left. Oh. Let me just do this row max. Just not change the parameter name. Row max.
Yeah, that's why I also used to just make the DP and the other ones. I don't have to pass down like 5 variables. But either one works.
Positional argument. Okay, we have a dice. We're forgetting our cache. Okay, the index out of range. For dice in 1 to 7.
Oh right, so your dice is 1 to 6, but you're
sorry.
using dice as an index, so it's off by 1.
Rookie move. That's
Yeah.
crazy. 0 to okay, yeah, to 6 here. Or just say 6. Everything wrong. What the heck? 34. Okay, let me think about it.
I mean, it's pretty complicated, so okay. So you have another error. I'll just point out to you. Maybe you have more, but in line 10, you're saying if my current number, like if I don't have enough rolls, I'll continue. But otherwise, when you DP, you're basically just like passing in the roll max.
-1.
All
Sorry.
the time.
Yeah, sorry. -1. Forgot that because that means like I chose it now. Okay, that helped with a few. Because that means I chose that.
No,
dice.
that wasn't the error actually. So by the way, so these dice are technically 1 through 6 or whatever, but you can actually just use 0 5. It's the same question. But the problem is, so if you don't have enough rolls, you're continuing. But what if you like? Let's say you're on a die and you do have enough rolls. Think about what you're doing. Like let's say you're on roll dice number 1, and you've rolled it 3 times and you can still roll it more. Like what would happen in your code?
I could still roll. Okay, wait, say it again. Like I'm on dice. Let's say I'm on dice 1.
Mm-hmm. And you rolled it 3 times, and you can still roll it more. What would happen in your code?
Okay, so pretend it goes 1. So it would.
So you rolled it 3 times, and then
it would recurse on that. So it would choose that dice again, 1.
Mm-hmm.
So it basically roll it again, like choose the roll and add to the path.
Yeah, so when you do this roll max dice -1, roll max is a starting array, so it would just like reset it all the time.
God. Yeah, you're right.
So for like a new one, it makes sense to do this, but yeah.
What we can do is like update the roll max -1 and then +1 after. Use it.
Well, can we just extend the if statement on line 12 and then like kind of have 2 cases if we can roll or not? Like if we do have the current one, if it's 0, continue. Otherwise, use the new number.
Wait, can you repeat that?
Yeah, so you're checking like, is this die the same one I rolled? So can we just extend that if statement to say like, okay, if that is the same one I rolled, if the rolls left is 0, continue. But if not, let's just update my number to what I had before -1. Does that make sense?
Yeah, I see. Like if.
Because line 17 basically just resets every time. So you would just be able to roll infinitely.
Yeah. If dice is equal to the current number, we're going to have what condition else? That makes it simple.
Yeah, you could do it that way too. Yeah.
So like result +1. Here, what we're going to do is like, we're going to take the rolls left -1. And then like, if we choose a different one, we kind of reset.
Yeah.
Oh my god. 111. Okay, let me look over this case. I didn't even know how to debug this.
Oh, so you forgot one last thing, but it's pretty simple. You just need to modulo the numbers. So that might be the case too.
Modulo 10. Harold, I'm getting cooked, huh?
Getting cooked. Okay, that it worked.
Hope so.
If not, there's wrong answer.
10 to 11. But yeah, this is such a low number. It should.
Okay, yeah. So let's see if let me read it some more. I didn't see anything else that was wrong. Huh? Number 6. I do think this is probably wrong. Well, I'm curious, like if we just get rid of that. Oh no, that just gives me the wrong thing. Okay, so 0 to 6, self to P. Yeah, you're like off by 1 somewhere for some reason.
Okay, 0, 1, 2, 3. Oh, because I passed in 1 here. That was a bad mistake. Yeah. I
Oh, I see.
passed in 1.
Okay,
Please work. Please
hopefully that'll
work.
work.
Let's go.
Please work.
You got time for one more? Holy crap. Any feedback on that one?
Yeah, sorry, I was talking to my brother. Yeah, I would say, so it's definitely difficult for you to get the dimensions for the DP. Like, you struggled there.
Yeah.
But I feel like the hints I gave you weren't that obvious. And you were able to, like, get the hints and get, like, unblock yourself. And then you were able to actually, like, code most of it yourself. You missed the 1 edge case. But, yeah, I would say this is, like, a harder problem. I do think, though, like, for like a harder company, or if they only ask 1 question, or like some Google thing or something, I feel like this is pretty reasonable. Like, it's not like some insane thing, you know?
Yeah. Honestly, I just haven't been challenging myself. Like, this is a good question.
Right. And that's the other thing I would say is, like, if you only do really easy problems, or, you know, whatever, it's kind of hard to get better. So I feel like if you do these more often, then you would just like see it faster, do it better, and make less mistakes and so on.
Yeah.
So yeah, I mean, you were getting a little bit lost in the end, but also it's kind of complicated, so that, like, I don't really blame you there. I will say, yeah, like making this DP outside maybe overcomplicated things. Like, I would just made it in here, and then you wouldn't have to pass down like 7 fields.
Mm.
But that's personal preference. Like, if you
Yeah.
can do that and you can do it correctly, then sure. So yeah, I'd say overall, like, definitely not bad, considering also you said you started DP like a month ago or something, right? Or like 2 months ago.
Yeah. Well, I did like I learned DP before. I just haven't really.
Mm-hmm.
I didn't brush up on it. Like, DP is not new to me. Otherwise, I would not have been able to do that at all.
Yeah, got meta in the bag. Let him. I mean, yeah, I guess the meta stuff is also kind of like it's kind of different criteria, right? This is more like, can you solve a pretty hard problem? Meta is more like, can you solve a medium problem but really quickly and like explain your code really well, and like it just tests for like different things. So
Yeah.
I guess this would be more like, I don't know, you get asked. I mean, I think like, yeah, like think like Google or something doesn't do the 2 problems, but they ask harder, and then probably some other quant or whatever, that type of stuff probably asks harder than meta stuff, I guess. I mean, meta you can also get asked hard. It's just like luck, right? So you can get kind of cooked if you're unlucky.
The thing is, like, why this is so helpful is you're giving me the hints that I need, right? If I was doing this myself and I got stuck, I wouldn't know what hints to take, or I would just get stuck and I'll be like, okay, I'll look at the solution, and then like that's like
Exactly.
even worse.
So you're still like challenged, where it's like, I don't tell you the answer.
Yeah.
I'm just giving you just enough to kind of like unblock yourself and keep going. So yeah.
But I feel like if I was doing this alone, that's why I struggle with these 2,000 Elo questions. Like, I just straight up end up looking at the answer if I can't solve it. Then I don't have to struggle through it the same way that I just did right now. But this I actually learned a lot, like understanding that the path is resetting. That's really important. Yeah. Should we do another quick one? Do you know any one that's like won't be too hard that we can squeeze in 20 minutes?
Like, so we can do another one. We can just see. So it's going to be the same Elo, but it's easier in my opinion.
Sure.
It's graph, so it's kind of like inflated Elo. So yeah. So I had 4. This is like the second, or it's probably the easiest one out of the 4. And then I'll yeah. Okay, so let me link. So it's 1761. You can just maybe add me to that one.
Yeah.
But yeah, I've been doing the 2000 plus. I feel like it's pretty good. It's like all like this one I did reasonably quickly. I do actually. The funny thing is, the harder ones for those are the like not DP and graph and stuff, because they're not inflated in ELO, and they're actually quite complicated. So yeah.
Okay, cool. All right, let me read into this one. Oh yeah, let me invite you here quick.
But this is what I was doing with the Q4s. Like, I would get stuck and read the solution as well, but they were so hard that like, even if you read the solution, it's still not super intuitive. And then I coded it myself, and I like explained and made a video. And yeah, if you do that for a while, you get really good. So
yeah.
All right, where did you add me into the meet?
Honestly, that question, I don't think they'll do. If it was an interview, they'd just make you do that one question.
No, yeah, it would definitely not be 2. Yeah, I agree. Like, if you had 45 minutes, getting that as like a 20-minute would be pretty ridiculous. So yeah.
Yeah.
Yeah. And then they just probably wouldn't give hints. They just give you like 45 minutes or 50 minutes. And then if they had to give you as many hints as I did, it would probably be a fail.
Mm.
But yeah.
Okay. Cool.
But it doesn't matter. Like you're not trying to interview. You're trying to like get better, right?
Yeah,
So
I'm just trying to get better.
Yeah, because if you only do things that you can like do in an interview and do really well, then like yeah, you basically never get better because you're just doing stuff you know already. So.
Yeah. Okay. So we're given an undirected graph. We're given an integer n, which is the number of nodes in the graph, and array edges, where edges are like the edge between two vertices. Indicates that there's an undirected edge between those. A connected trio is a set of three nodes where there's an edge between every pair of them. So this is a connected trio. The degree of the connected trio is the number of edges where one endpoint is in the trio and the other is not. Return the minimum degree of a connected trio in the graph, or -1 if the graph has no connected trios. So, okay. Let me parse out some of the problems or everything in the problem statement and then actually look at the example. Mm-hmm. So yeah, we're given an undirected graph. We're given an integer n, which is the number of nodes, okay? And then we're given a bunch of edges. Number of nodes. And probably the number of nodes is like... Number of nodes. Does it matter? And then each edge goes to ui to vi. Okay. So the n is one index. So it's maybe 1, 2, 3. So if we say n equals 6, that means we have nodes 1, 2, 3, 4, 5, and 6. Right? 1, 2, 3.
Yeah.
And then we have edges now, right? Edges. Right. So we have edges. Edges is gonna tell us the different nodes of like from 1 to 2. Okay. Yeah, 1 to 2. Okay. Yeah, edges is the undirected thing. So that makes sense. We have our adjacency list, or how we build our graph. So a connect tree is a set of 3 nodes where there's an edge between every node. So this is a connected trio right here. Let's see.
Yep.
Let me see. The degree.
Yeah, so there's only one trio in the first example because there's only like that triangle that's connected.
Okay, the degree of a connected is where there's an edge between every pair of them. Okay. The degree of a connected trio is the number of edges where one endpoint is in the trio and the other is not. Okay, one. So I can't really see the bold, but I see it now if I stare at it.
Oh yeah, yeah.
So what's it called? So the bold. So these are. So we just need to find all of the. Okay, so this one is 3 because there's one connected trio, and then the edges outside of them are just 3. So we need to return the minimum degree of a connected trio. So, so what I'm thinking is, so let's look at this example. There's 2 connected trios. Actually, there's 3 connected trios. Okay, this connected trio has 0, 4, 1, 3, right? But then there's this connected trio. There's disconnected trio 2, 5, 6 and 5, 6, 7. What about 2, 6, 7?
So 2, 6, 7 is not, because they have to all be connected.
Okay, yeah. Okay, yeah. And then we just need to. So what I'm thinking is maybe what we're gonna do is the first step is like find connected trios. And then once we have a list of connected trios, like loop through each one to figure out the degree of those trios, right? So I think
Yep.
the hard part is just finding the connected trios and like deduping them.
So, can you explain what you mean by deduping?
Dedupe those. Like we don't want to 415 or 413. That's one connected
Mm-hmm.
trio, but we don't want to look at that twice. I mean, it doesn't really matter. Like we can look at the basically what I'm thinking is like for each node we see the connected trios that it could form.
Mm-hmm.
So with one, we can look at its edges and try to form a connected trio,
Mm-hmm.
and then we could figure out how many connected trios are in one,
Mm-hmm.
and then figure out the out degree or the degree of that trio, and then we could do
Yeah.
that. We can loop through each node and kind of do that. So loop through each node,
Mm-hmm.
and then maybe we can speed it up, but like loop through each node, find connected trios, and count the degrees. And like there might be duplicates because pretend I look at three and I see
Mm-hmm.
that it's part of one connected trio and I look it up again, but it shouldn't affect the actual result.
Yeah. Like if I look at like 265 or 562 or whatever, like it's the same. So it shouldn't matter at all.
Yeah. So yeah, this is what
Okay.
I'm thinking right now. Find connected trios and count the degrees. And maybe one way that I could find the connected trios is like maybe find cycles of exactly length three. Because if I find a cycle of exactly length three distinct nodes, well, no. Wait, fine. Wait, let me see. How do we know something is a trio? I mean, it is a cycle for sure. I guess
Yeah,
we
so
need
what would
to
be like the easiest thing you can think of to figure out how something is a trio?
like we could just straight up like be
Like what would be the brute force of checking if something is a trio?
like for each neighbor, check if it has a neighbor that points back at me.
Yeah,
Yeah.
well, they're all gonna because it's undirected. But like, let's say, like, if the problem was just give me the number of connected trios, including duplicates or whatever, in this whole thing, what would be the brute force of that? Would like doing no traversal or anything? Can
Okay.
you think of something?
Wait. Could you repeat that question? Sorry. Okay.
Yeah, so it was like if I just say like give me the number of connected trios, not accounting for duplicates, so like 256 and 265 are different. Like what would be the brute force way of doing that without like doing some kind of graph traversal and like looking for cycles and things? Like what would be even easier, I guess?
I mean, like the way that I think is would be the easiest for me is
Okay, what would be the
just
easiest?
straight do a DFS that could only go through three. Like basically look for cycles of length, or if we could find a cycle by only traversing three nodes.
Okay, so how would that look like, I guess? So we start at some node and then we see if we can find a cycle by traversing three nodes.
Three distinct nodes.
Okay, sure.
So basically, yeah. So basically, what I would do is, I mean, the brute force way would be like pop one in there and then pop all of its neighbors,
Mm-hmm.
or basically look for two neighbors that point to each other, kind of thing. Or look for without
So
a graph.
neighbors will always point to each other, but I guess to give you like if I give you three nodes X Y Z,
Yeah,
can you tell me if they're a connected trio or not quickly?
yeah. Like well, if I'm given X, right? If I know X, I can
Mm-hmm.
just pick two neighbors, Y and Z,
Mm-hmm. Mm-hmm.
right? I know I'm connected to X or Y and Z, but if Y and Z
Mm-hmm.
also connect to each other, if there's an edge there, then I know that's a
Mm-hmm.
trio.
Okay, yeah, that makes sense. So you're saying like take node X, go
Yeah.
through all the neighbors of X,
Like a double for
uh,
loop through the
with a double
edges.
for loop. Okay, and so what would be the time complexity there?
Like if it's a fully connected
Yeah,
graph,
fully connected. Sure.
um, like, like if we go through n nodes and we
Mm-hmm.
do a double for loop through the other ones, it'd be like that'd
Mm-hmm.
be like n squared is like m cubed. I feel.
Right. So yeah, so I guess we can look at the constraints and ask ourselves like, is that going to pass? Because I feel like for hard problems, like you generally just want to start like if you can pass the constraints, you're pretty close to optimal already.
I mean,
for
I
hard
feel like with
problems.
n equals to 400,
Mm-hmm.
and there are no repeated edges,
Mm-hmm.
I feel like it might be past these constraints. The constraints are very small.
Yeah, exactly. So this will actually just pass. So let's try to get a solution like that where we literally just brute force the trios, and then we can try to do some optimizations after that.
Okay, there's like a DP kind of thing. I mean, we might be able to cache, but or like remove like dedupe to avoid.
So let's focus on
Yeah, I see what you're
not
saying.
deduping maybe, and then we can talk
Yeah.
about deduping. Because
So
like you said, like not deduping doesn't matter because like if I visit 123 or 132 or whatever, it'll give me the same answer, and I'm just looking for the minimum, so I don't need to know how many.
yeah.
Yeah.
Okay, so we're gonna loop for like result equals float infinity because we're trying to
Mm-hmm.
minimize some value. So what
Mm-hmm.
we're gonna do is I mean, do we need to parse out an adjacency list here? Let me see. I guess we might need to. Do we need to parse out? I guess because we're only given the edges, so we need to parse out an adjacency list. So what we're gonna need to do is, um, for edge A to edge B in edges, we're gonna build an adjacency list. So we're gonna say from collections. I know this is already imported, but I like to just make sure I
Mm-hmm.
remember the syntax. But what we do, we create an adjacency list, default dict with integer, or sorry, it's probably just like a set or a list. Probably just, let's just go with a list.
Okay.
So we could do the double for loop better. But what we're gonna do is in the adjacency list, what we're gonna say is edge A has a neighbor of edge B and vice versa because it's undirected.
Mm-hmm.
So that will parse us our adjacency list.
Mm-hmm.
And then what we'll do is we'll just loop for node in range maybe 1 to n plus 1 because it's one indexed.
Mm-hmm.
I think it's one index, right? Just say that at all.
Yeah. Yeah. No, they're all one indexed.
Um, for node in what we're gonna do is we're gonna pick our node. For every node, what we're gonna do is we're gonna double for loop through the neighbors. So we're gonna be like for neighbor A for I in range. Or we're gonna be like let's get the neighbors first, right?
Mm-hmm.
Neighbors equals we'll access the adjacency list. We'll grab the node. That will give us a list of the neighbors. And then what we're gonna do for I in range length of neighbors. For J in range like I to the I plus 1 because we already chose I to the length of neighbors. We're gonna do this double for loop, and what we're gonna do is neighbor A, neighbor B, and what we're gonna do is we'll say neighbors at I and neighbors at J. So that will give like we're positioning the two nodes. So I already know I'm connected to these two ones. So what I'm gonna do is I'm gonna be like I need to check if they're neighbors. If but they're not, like with the list it's gonna be inefficient, but we could speed that up. But we just need to check if they're neighbors of each other. So if adjacency list of if the neighbor B is in the adjacency list of neighbor A, so we get the adjacency list of neighbor A, these are the neighbors. So if A is pointing to B, like that's actually a connected component.
Mm-hmm.
Like
Yep.
that's a trio.
Okay, so if it's a trio, how do we actually calculate this thing that we need?
Yeah. So we do if it's trios, we kind of need to subtract like 3. So we need to figure out all of the wait, there's gonna be a. We could just calculate, add up the length of the list for each of the edges here.
Mm-hmm.
Add up the neighbors and do some math to like delete out ones that we know are each other. So pretend for this one, it has like 3 edges. So I think we
so
just
let's
have
take
to
a look
minus
at maybe
9.
example.
We just have to minus 9.
Let's take a look at example 2 because that kind of shows the ones we need. So the one on the left, what's going to be our total? Like how many edges does each one have?
Yeah, it's gonna be 9. So it's gonna be like 1. Or wait, this has 2 edges.
Mm-hmm.
So this one is gonna have. Let's look at a simple case.
Yeah, that's like the simplest one. That's why I want to do that one.
So we'll do like 4. This is gonna be like 1 and 3.
Mm-hmm.
Then we're gonna have 1. 1 is gonna have 4 and 3. And then 3 is gonna have 4 and 1.
Mm-hmm.
So if we add up all the edges, then we kind of just need to delete these edges. 4 to 1. Because those don't count. So we just need to minus 8. Kind of thing. We just say like, we can loop through the edges.
So how many edges do we have total in this thing? Like in this, like how many edges does each node have? I guess
8. Or sorry, 6. Sorry.
Yeah. Okay.
6. Sorry. So basically, what we need to do is like we need to sum all the different nodes, the length of this, and then minus by 6 to remove the ones that are connected to each other, and that will give us like the ones that are the degrees outside.
Yep. Okay, so let's do that.
Okay. So what we're gonna do is like total sum equals 0. Let's say for Roger, what's up? So for neighborless, wait, what are we doing? We're looping through. Okay, for just say like current node, so current node, whatever, and then we're gonna loop through. We're gonna loop through the current node. We're gonna loop through the neighbor A, and we're also gonna grab the neighbor B. And what we're gonna do is we're gonna say total sum plus equals the neighbors of that current node, like minus 2 or something. That'll get us there. And then basically what we do is result equals the min of result and the total sum. So yeah, this captures degree. Yeah, I think just that simple for now.
So let's see if we have any problems here.
We
can try to run
it. Oh shoot, I did -1. Wait, index out of range. Where's neighbors?
So what is neighbors?
Oh, sorry. This is adjacency list. And we have to capture the length. It might be slow. Should we try running it on the big test case?
We can try, yeah, sure. And then we could see like what we could optimize.
Yeah.
I think you mentioned some stuff.
Like deduping the set, like adding a set there, like add a set.
Yeah. So yeah, I think adding the set, like what do you think? What do you think matters more? I guess. Oh, you got. Okay, so you can fix that one first.
Okay. If none, if so.
Okay.
It's very slow.
Yeah. So what do you think will?
Wait, what happened here? Oh, sorry, negative.
Oh yeah, you need -1 instead of none. Okay.
Like
What do you think is going to make a bigger difference, deduping or adding a set?
Probably deduping.
Okay.
Wait. Let's see. Maybe adding a set is gonna make a big difference here.
Yeah. So what would this be with a list instead of a set?
Like then just like searching for.
Right. So this would be like n
This
fourth
one.
or something, right? With
Where-
a list.
where
So I think
here,
a set
like-
would be more
For neighbor
beneficial.
B, this one, right? This function right here is like then.
Mm-hmm. Yeah. So I think the set would actually be better. Plus, it's easier, so we can do that first.
Okay, let's go set. Add. For node and for nabes equals. I'm gonna do. Let's just turn this into a list.
Okay.
Dot keys. Neighbors.
I don't think you need keys. I think just list adjacency list nodes are already a list. I think that'll just give you what you want.
Then maybe we can dedupe worst case.
Mm-hmm.
Let's see. Oh my god.
So where are we? Adjacency list. Maybe you can just try running this one test case and see if we're close. So add that test case to your and try to run that. Because yeah, I'm curious if you're like still way off or
right there.
Okay. So we're pretty close to getting something.
Then
So yeah, so
maybe deduping.
Yeah, deduping, and then so for the set, are we using the set everywhere, or are we using nabes somewhere still?
We're using nabes.
Like, are we iterating nabes I? Yeah, what does that do? What does line 29 do?
Well, it picks like two random neighbors.
Oh, okay. So that shouldn't matter. That shit's fine.
And then we're seeing if they're actually connected to each other, and if they are, then we do this. But for here we kind of loop through the node. Maybe we can cache that. Oh no, like the.
So let's try. Yeah, I guess let's think about deduping. I think this is also one of those questions that like barely passes, so it's kind of annoying. So
if I run it, or like there's some parts that I could just speed up here.
Yeah. So basically, like, so how could we dedupe? Or like you said, the problem is like we're hitting all three. So how do we like do the earliest possible dedupe, and then maybe, yeah, like I guess what optimizations can we make to just like dedupe and also break as fast as possible? I guess.
Wait, sorry, could you repeat that?
Yeah, so what are some optimizations we could do to dedupe and also break as fast as possible if we do have duplicates? Like, ideally, we don't want to have like duplicate, not duplicate, duplicate, not duplicate. Like, is there anything else we can do? Or I guess let's think worst case. Like, worst case, let's say the graph is fully connected. How can we optimize that to dedupe, not have to do so many searches, and then yeah, like things like that. Like, because that would be the worst case, right? The graph is fully connected. That would be the slowest. So how do we handle the deduping and then maybe restructure our code, or just handle deduping, start off with there? Because right now we're just trying every three possible.
Yeah, if I do 4. Okay, let me think about the first one, deduping then. So if we do 4, 1, 3, do I need to check 4 again? Well, I need to check 4.
Yeah, so like if you do 4, 1, 3, you don't want to check 4, 3, 1 and then 1, 4, 3 and so on, right?
Yeah, maybe we can sort those 3 and then like have a set. It's like we need to check. Wait. But then this part is not even that much longer. Like always save from the dedupe. Because we still... Wait, maybe we might need to able to update the set. So it's like 4.
Yeah, so we're still looping, like, yeah, so you're kind of on the right track. We're looping through all the neighbors twice, no matter what. So can we kind of like not loop through all the neighbors twice and maybe do some like you said, maybe sort or something? And then so we don't have to just like loop through all the neighbors twice. Like we can just say like, okay, for the, like when this doesn't work, nothing past this will work or something like that. You see what I'm saying?
Yeah, if nothing passes. Wait, sorry, could you repeat that? I didn't get it.
Yeah, so we have these like 27, 28. We're checking through the neighbors twice. So ideally we want to have something like these are all valid, and then once we get past some number, we would just want to say like, all right, if this is not valid, then like the rest of them aren't either. Ideally, instead of having like this works, this doesn't, this works, this doesn't, because that doesn't really save us anything.
Basically, you're saying here, if this doesn't work, like an early stop.
Yeah, have like a break or something. Yeah, exactly. Yeah. Is there any way we can like structure our data or something, or maybe redo this? Yeah.
Like we're already looping from 1 to n.
Mm-hmm.
Right.
And the same thing through the neighbors. Like we can have an earlier turn there. Like for example, so I guess in general, like let's say you're doing like a subsets problem, and I say like, you know, give me all subsets, but I don't want 134 and 143 and 341. How would you handle that? Like, what's the easiest way to handle that?
Like sorting it usually.
Yeah, exactly. So is there any way maybe we can like, when we make our graph, like if we're on a 1, for example, if we just say like all our trios are in increasing order or something like that, you know, and then like if we're on a 4 and a neighbor's 1, we could just be like, well, we don't like, that's never going to be good because we're only going to do 1, 3, 4. We're never going to do like 4, 1, 3 or anything. So is there any way we can like modify a graph a little or some other, or maybe change these for loops around to avoid like have earlier turns everywhere?
To avoid earlier turns everywhere, yeah. I think we'd probably just need to sort the trios or something.
So instead of sorting the trios, I meant like, can we sort the edges or nodes or nodes?
Like here, right? Here in the neighbors, sort the nodes in some way.
Yeah, like let's say, like for example, an easy example would be like, let's say 1 has neighbors 3 and 4. If we just store the neighbors in like a sorted order, then whenever we're at a node and we're going through the neighbors, we can just say like whenever we hit a neighbor that's smaller, we'll just stop.
I see. Or no neighbor that's greater, or we need to start like if we're at 1, we should only start from neighbors
that are greater or something. Yeah,
and we could just skip.
Yeah,
but then we'd skip
the rest. Yeah.
So let's do that.
Okay.
Sorted. Wait. Sort. That'll give us our sorted neighbors, and we'll say if I is less than the node, less than or equal. Continue.
So do we even need to continue, or can we just break because we're sorted? Or I guess like maybe like which way do we want to do it? Increasing or decreasing in your case when you're sorting? So you want it increasing. So like if we're at a, or I guess we can do it. We can do a continue. I think that's fine. Okay, let's try this. Yeah. So essentially, when our neighbor is, or should it be I or should it be the value?
Yeah, you're right. Damn, getting cooked.
Cooked. There's actually like a way easier way to do this one as well, like that I can show you.
This was way more complicated. Yeah. Let me get this. Nice. Okay.
Did it work?
Yeah. Okay. Because the video's already 1 hour 10. I might let's just close it off with some thoughts, and let's stay on so we could talk about. So you could just teach me the other stuff. Maybe that could be enough.
Yeah. So some thoughts. I mean, I do think this one is just kind of hard to hit the runtime to pass. But some thoughts for this one is, let's see, like what problems you had, I guess. So definitely, I would say some problems you had was you were kind of stuck in the beginning to like you were trying to do things that were too complicated. You were trying to like if you were trying to run through the whole thing and get all the cycles or something, that would be kind of difficult. So you need to try to recognize like what's the simplest way to solve a problem, and then like is this going to be fast enough. And so
I see.
especially for these hard problems, I would try to focus on that. Like, what's the simplest way I know to solve this problem? And then like, is this going to be fast enough to not get TLE basically? And yeah, I guess for LeetCode, it's basically kind of like when you are doing the harder problems, you kind of have to look at constraints. Like there's no way around it. You have to use your constraints and like estimate a complexity, and then like think if will it pass or not.
Yeah.
And the nice thing is for the hard problems, like the constraints are already going to be pretty tough. So as long as you can just like pass the constraints, your solution will be close to optimal already. Like for easy, you can do whatever you want; it'll pass. For hard, that's not the case. Um, and then let's see some other stuff. Yeah, you're definitely having trouble like figuring out like how do I traverse neighbors? How do I optimize this a little bit? But the rest of it, yeah, I'm trying to think like where did I give you the hint in the beginning? I guess this is also one of those things, right? You didn't write that many notes, and I didn't write notes on my side.
Yeah.
So then, if I do have to write, like, if I was actually interviewing you, and I went back like 3 days later, it would be hard for me to remember like what you did wrong.
Yeah.
So that's why I'm like in a real interview, I would just have notes of like what you did wrong and what I gave you hints with. Um, but yeah, you did figure out like, okay, I can just find all the trios, I can count the degrees, and then I can like just do a subtraction. You did figure that out like pretty well. So yeah, I think overall just maybe write code that's a little bit cleaner. Like you missed like missing the set, I would say is kind of like the big one that you screwed up.
Yeah.
The deduping, you also did realize that like if I don't dedupe, it'll be the same it'll be the same answer, so it's not that much of a difference. But missing the set, it basically just gives you like another factor of complexity, so that's a big one. And yeah, I would say yeah for graphs, just try to figure that out, and then the rest. Yeah, I'd say the rest was pretty good. This problem just has kind of like a stupid runtime you need to pass, so that's just more on the problem, not on you. And yeah, you also did I think figure out like the sorting part, at least part of it. I did have to give you like a few hints.
Yeah, you give me a ton right there, but yeah, that's
Yeah,
good.
but overall, like once again, like I didn't have to do the problem for you. Like I can give you a hint, and then you can go from there. And I think for these hard problems that you're not used to, that's like really good. Like I wouldn't expect you to do all of these like with no hints whatsoever. So yeah, exactly. You're able to, and that's kind of like I think that also shows like the actual engineering skill, because like on the job you're going to be stuck a lot, and it's like, can I give you a pointer and then you can take it from there, or are you just always stuck? You know?
Yeah.
I think
Nice.
that is something like people look for. And then yeah, as far as yeah, I think that's honestly that's honestly most of it. And yeah, like you see, like I do think if you do this level problems consistently, you'll get a lot better. So I mean, that's just up to you. Like, do you want to or not? But
Oh
yeah,
yeah, I definitely want to. Okay, that makes sense. I think, like with deduping, like I'm just not you. You don't have to do that much in the medium questions. I mean, you do, but not as
yeah, no,
often.
this one has hard constraints that like you need to do a lot to make it pass. In the mediums, like it's never you don't really have to do this kind of stuff. Yeah.
Sick. All right, cool. I'm gonna end the video here, and then yeah, let's talk about your solutions.